Hi everyone, good afternoon. So today is somewhat a unique talk because it's a hybrid. So my mom is remote right now in Brazil, and we're gonna have this exploration together about what has changed and what hasn't from Fortran to Python, specifically within the context of scientific computing. So my name is Rodrigo. I'm a QA engineer. Is it better now? Yeah, I think it's better now. Okay, so my name is Rodrigo. I'm a QA engineer at Posit, and my mom is a professor at the university in Brazil, at the Federal University of Bahia, and she's the best person to introduce herself. So let me just go to the next slide. Yeah.
My name is Helianildes. I graduated in chemical engineer in 1987. I did my Master of Science in mathematical simulation with Fortran, and also my Doctor of Science in modeling and mathematical simulation with Fortran using artificial neural nets and principal component analysis. Well, as you know, we at first we used punch cards because we didn't have a personal computer at the university, neither at home. So it was very, very hard to work to do, but it was worthwhile because we could learn a lot about computer program, and Fortran was an easy language to to write and to debug. I think that it was a good time at the university working with computer, even though we don't have the the utilities, you know, mm, to do as fast as you could. But this was a very, very good experience.
So this is the context of this talk to, in a way, how things have changed from the times of Fortran, especially when, and I mean, just to clarify, Fortran is well alive today. People still use it and so on. Of course, the ways and the daily workflow is a bit different today, but it's still well alive and well used for scientific simulations and so on. So just to contextualize this story, we decided to frame it as a story of um, like us as a mother and a child. So that's some photos, some old photos, and just for context, I remember being as a child seeing some serpentines all over the place, and I couldn't really understand what they were, and sometimes I would um, like draw them and protest bad time, just say, oh, I would just go to sleep once you finish drawing the serpentines. And I never knew what this represented or what this meant. And it took a while until one day, um, yeah. So I thought that drawing I was helping somehow. And one day I finally learned what these endless serpentines were. And those were an interesting thing because it shaped the relationship I have with my mom to this day. Also made me a late night sleeper because seeing her struggling with the computations and everything, I would often just stay up late. And the answer was in her thesis, which focused on mathematical methods for simulations of cracking of a chemical process, and she's the best person to talk about that.
5 years later, Rodrigo discovered that my thesis work was to model and simulate the EDC cracking in a furnace coil. and we used artificial neural nets and principal component analysis to model and to simulate the system.
Yeah. So just for context,
Five,
the serpentines that we're referring to were essentially, I mean, besides the integrals, there were also models of furnace coils, and which are very important in the context of modeling the cracking, the processing of chemical processes, and so on. So those were the serpentines, and in general, how to model chemical process in a furnace serpentines, it requires a lot of Fortran, and I want to use that as a segue for just a general overview of what is Fortran. So Fortran was released in 1957 by IBM, stands for Formula Translation. I know a lot of you might have heard before or might have used it and so on. And it's very interesting because it's extremely fast when it comes to execution of numerical computations, hence why it's very popular in science and engineering. And one overlooked aspect of Fortran that we think it's worth mentioning is that there were a lot of women involved in the Fortran community, especially during the early days. Unfortunately, they were often underpaid or undervalued, but there was a heavy involvement of women in the community as well. So here it's just an overview of the typical process that my mom would go through when writing and debugging Fortran in general. So I'll play.
well, at my time at the university in 1980s until 2000, my life was like this. Write code on paper because no computers at home. After figuring out what to do with my children, I had to go to university and type code in a punch machine, line up to punch cards, submit deck of punch cards to operator, and finally go home and make sure if children were alive and wait for the next day.
Yeah. So that was the typical workflow, and of course we can notice many differences with today in terms of practicality, but this at the core of it, the aspect of the importance of Fortran in scientific computing remains like well alive and so on. So here, this slide is more to clarify the differences between Fortran and Python and to contextualize that those are not necessarily like competing languages in any way. It's more like it really depends on your use case. So if you are going to use for numerical computations, for example, like Fortran can often yield a better performance as we're going to show later with a demo. So Fortran, in terms of compiled performance, is highly optimized for loops. It's used in legacy code, especially for science and engineering. It's ideal for simulations, and it's based on static typing. Whereas Python, it's easier to learn. It has very rich, vast libraries. However, it process is slower with loops. It's great for orchestration, and it's widely adopted. And yeah, and with that, we developed that chemical ordinary differential equation example just to compare the performance between running the same problem in Fortran and Python. And we thought that could be interesting from an implementation standpoint in case any of you ever want to run like Fortran code in Python. So first, just a brief description. about the problem.
The EDC cracking is a reaction that produces monovinyl chloride. This reaction occurs in a furnace coil, and the temperature and pressure should be maintained in a range, in a specific range, because during this reaction we can have some byproducts that could damage the coil.
Yeah, so essentially that's the overview of the problem. And there are a lot of factors that are explored in this specific problem, including the ones in my mom's thesis and in other works and so on. Here we are only interested more in a kinetics exploration. So that's why we mentioned the rate factors, K1 and K2, and the concentrations. So setting up the OD system, we have an equation for consumption of EDC, an equation for the MVC, which is an intermediate, which gets converted to HCl and other byproducts. And we have an equation for HCl accumulation. If anyone is interested in the code, in the link from the beginning, and in my GitHub, there is the full repo. Yeah. So in terms of, so as I said before, like here we're not gonna get into the syntax necessarily, but just the high level picture of how we're doing. If you're interested in the syntax, just check the GitHub repo, and I think that will be helpful. But in general, just for running Fortran in Python, first we start with the Fortran code. We implement a subroutine in the F90 script to solve the system of ODEs using a numerical method. Then we compile with F2Py, which is available in NumPy. And just as I put in the README the instructions to do that, just as a heads up that they recently changed the way their backend works when compiling. So you might need to install other libraries like Mason and Ninja, like to brew install or install it through another method, just to make sure it works. The README instructions in the GitHub are up to date, and if you follow them, it should work. So then it generates a compiled SO file if you are in a Mac, and then that's the cracker file that you can use to import the code and the subroutine into the Python script. And then you're able to use it within the Python script for your simulations and benchmarks. And just to confirm that the performance-wise, you can see a significant difference, which essentially shows that you're actually running Fortran instead of running Python or any weird translation method. So those are just the results of the simulation, just to confirm that we are getting the results for both Fortran and Python. And then in terms of performance, like I said before, it's a bit ridiculous to compare the two because the applications are very different. But just out of curiosity, we decided to run through a lot of steps to see the difference in computing times between the pure Python implementation versus the Fortran implementation. And we can see that it is very significant, the difference going up to about 700 times of difference, which it's expected due to the number, how it's a differential equation with a lot of steps and so on. As we increase the number of steps, we expect that this happens. Yeah, and just a few, like before, um, yeah, before heading to the conclusions, just an observation as well that they there are nowadays other languages that try to solve the gap in numerical computing and simulation. One of them is Julia, for example. There was actually in Pittsburgh this week a Julia Lang Global Conference, and there's a lot of interesting work going on to bridge this gap between computational speed, numerical solving, and so on. So that's something to look for. In terms of conclusions of what we did a chemical process modeling, which you can find more details in the repo, with the Fortran integration, in which we noted a significant speed up for the Fortran version of the script, up to about 700 times more. And we use Python for prototyping and visualization. And even for visualizing the Fortran output, of course, we had to use Python. We didn't consider that as part of the script. We are only considering the computational, the numerical calculation part. And the key takeaway here is not, again, one better than the other, but rather how we should select the right tool for the right job. And yeah, they can be very complementary. And what we are interested here as well is how some tools can be used together in the future to bridge the gap between potential problems that exist. And in terms of yeah, and just in terms of the big picture about how have coding and scientific computing changed from the Fortran times, I wanted to share this video which I found quite interesting. So essentially, here there's uh, the card, the punch card that they used to use, and you had to put them in order. And if, let's say, you dropped your stack of cards, maybe your code would be out of order. So then you always had to make sure that my mom told me that she used like elastic bands to wrap the cards. And yeah, and she talks a little bit about the process before writing in the punch card itself, before punching the cards.
Do you know what's this? This was the paper on what I had to write in my Fortran program. Before I punched the cards, I had to write down on a paper all the codes and then punch the cards and go to batch my program in a deck desk. Then, after half an hour, I I came back and see if this program was aborted or not.
And then, so we are essentially going from Fortran times, and like was mentioned before, the Fortran, just in a different way, is well alive today as well. But processes that were very intensive from a wo- working standpoint to days that we have modern IDEs, Python notebooks, AI, LLM assistants, and so on. And it's just mind blowing how much scientific computing has evolved throughout the a very short span of time. And nowadays we have all these tools available. And I don't know if you're familiar with all these tools, or I mean, I know a lot of you use at least one or two of these IDs. And I've also found very useful to explore the different IDEs and to actually go into to try to understand how they operate and how they can help my workflow. So that's something I've found interesting to do, especially with the AI LLM assistants, because I'm noticing like a shift in perception in which it almost feels like an IDE that nowadays it feels like an IDE that doesn't have an LLM assistant is not a complete IDE. It almost feels like people are switching more to um, having that as part of the concept of an IDE, which is something surprising and new to me. And so that's the repo that we used, that we pushed, and for the references. And we wanted to make time for questions just because we thought that as part of our conversation, that would be the most interesting part. So if you have any questions, that would be interesting. Yeah.
I,
Okay, let me just a second. Any other questions? I'll answer the question. Yeah. So
I think that I should answer these questions or not.
it, sim, and let me.
Can you repeat, please, in Portuguese, because the noise is.
Okay. So this is,
What is?
I think this is the most exciting part of the presentation because that's the actual like Q&A. So yeah. So ele estava perguntando como code reuse, a reutilização de código, funciona com os punch cards.
Como?
Com os cartões, como é que funciona a reutilização de código, de funções? Você pode reutilizar de um cartão para em outro código, em outra uma subrotina, por exemplo?
Ó, pode. O código, ele funciona justamente pela perfuração, né? Então, você tem o cartão e o cartão é perfurado e aí você tem uma subrotina. Você pode pegar aquele conjunto de cartões já usados e testados e usar em outro programa principal. É só você chamar aquela subrotina, tá?
Okay,
É,
let me just translate this
você só
part.
tem que. Espera aí um pouquinho. Você só tem que ter cuidado com a numeração das linhas, né? Para não colocar referências cruzadas e essas referências cruzadas se misturarem ao programa, tá? Por isso que o código, ele, quando é perfurado, você usa uma indentação, você usa um recuo, você usa numeração de linhas, para que a programação fique estruturada. Na verdade, a estrutura é feita pela pessoa que programa, né? Você já usa aquela parte da indentação dentro da própria estrutura do Fortran.
Okay, I'll translate that. It's a very long translation. So actually, the code is already it relies on perforated cards that are part of one stack of cards, for example, and you can use that a subroutine, for example, as part of another sequence of cards. So you can essentially, since it relies on the perforation of those punch cards, you can actually reuse it across different um, piles of punch cards, of like functions and so on. So, tá mais ou menos correto?
Sim.
Okay. And
Uma
any
outra
other
coisa
question?
adicional é o seguinte, não
Fale em
sei se vocês
inglês.
sabem.
Tente falar inglês.
Another thing that I should remember you is that we use here the holarity. The holarity is the salary that you get, the money that you get from your work. Um, you receive a receipt monthly. Um, fifth, 50 years ago, you have to receive a paper, and this paper you call it olerite. The olerite was made from the punch cards, okay? And it was a very long time ago. So they program what you should receive with your hours of work, and then you receive the olerite, the paper on what you have your monthly salary. Another thing here in Brazil that if you want to win the lottery, I think that's the name of a film. If you want to win the lottery, so when you go to a lottery here, you have to take a card and you write down the numbers. We make, como é que fala, preenche o número, Rodrigo?
You fill in the numbers.
You fill in the numbers of a sequence from 0 to 60, and then you give it to the receiver. And this card is going to be punched, and then after that, when they choose the numbers in the lottery, they can know who wins or not. So, 50 years ago, if you would like to win the lottery, you should use uh, punch cards at the computers.
Any any other quick questions? We have just 3 minutes left. Entendeu a pergunta, mãe?
Não, você pode repetir?
Como era o processo de debugamento com os punch cards? Se você escrevesse um código errado, por exemplo, como é que você faria para conseguir corrigir e o processo de debugação em geral?
Você fazia assim, ó, eu ia na máquina, escrevia tudo, perfurava, aí entregava para uma pessoa que tinha o deck 10, que era o computador, tá? Então, nesse deck 10, depois de 15, 20 minutos, eu iria lá recolher o meu papel. Então, eu recebia como se fosse uma lista contínua de papel, com o programa todo impresso,
Uh, so,
e linha a linha.
so she would go to the machine, get an output line by line of the scripts, showing o, mostrando o que aconteceu com cada linha,
É,
showing what happened to each line, and then she would go to the DEC dice, which was an old computer from IBM, I think. Um, yeah, and then she would essentially. Aí você faria o quê?
and then I read all the code they gave me back and see what was the mistake. Normally, in each line, if the line passes without mistakes, no problem. But if the line has a mistake, he would recognize and say, well, there's missing a parenthesis, too large column, and so on. Entendeu, Rodrigo?
Entendi.
Pronto.
Pronto.
Rodrigo, I hope you'll be around to answer any other
Mm.
questions that folks in the audience might have.
Eu tenho uma questão. I have a question.
Mãe,
Well,
o tempo.
yes, I know. Why do you do so fast my Master of Science and Doctor of Science? I think that I should know you before because I think that nowadays the languages and the processing are too fast. So I should think it was waste of time for me. No, this wasn't, I think so. And I think that could you explain me how could you be so fast obtaining that graphics of the reactions?
So, como foi rápido para conseguir? Eu vou explicar depois, porque o tempo já deu. Okay, she's asking me a question. I will explain to her later because we are out of time. And she's whatever I answer, she's gonna point out something wrong I did. So,
No, you didn't do wrong. Thank you very much.
pronto.